In part 1 of this lecture, we discussed using the alternating series test to determine if an infinite series converges. Now we're going to shift our focus to classifying a convergent series as either absolutely or conditionally convergent. So to begin, we start with an example of a series that will have both positive and negative terms, but it's not necessarily an alternating series. So with this sign that shows up in the numerator, I know that at some point the terms of this series will change sign. Some of them will be positive and some of them will be negative. And we know that because of the nature of the sine function. We know that the sine function bounces up and down between positive 1 and negative 1. So this is not an alternating series. So the alternating series test will not work in example 4. To help us figure out whether or not this series converges, we're going to consider this variation of the series where we have now applied absolute value bars around the term. So this guarantees that all of the terms of this series are positive. Mind you, with those absolute value bars, it means that the graph of sine would look like what's in red, the graph of the absolute value of sine. Everything that was under the x-axis would now be above the x-axis because everything is positive. So all of the terms of this new series are positive. So let's figure out whether or not this series converges or diverges. I'm going to use the direct comparison test because I do know that the absolute value of sine, so that's sine with the n inside of it, I do know that that's going to be less than or equal to 1 because the sine function does not get greater than 1. With that known, I can now come into this inequality and divide both sides of it by n squared. To be clear, we're allowed to divide by n squared and not change the direction of the inequality because we know that n squared is positive. And the whole reason that I divided by n squared is because now I have the exact same term that we have on the inside of our series. So what we have found on the right side, this 1 over n squared, is larger. Let's think about whether or not this series converges or diverges. This is a p series. P is equal to 2. Which is greater than 1, and so this series converges by the p-series test. So we have found a larger convergent series. So by the direct comparison test, the series from 1 to infinity of the absolute value of sine n over n squared must also converge. Because if the terms of this series are smaller than the terms of the green series, and the green series converges, then the blue series must converge to something smaller. So how does that help us? Because remember, we started example 4 with trying to figure out convergence or divergence for this original series that I just highlighted in yellow. We have now said that the series, when we apply the absolute value, we know converges. This is followed by a theorem on the top of the next page that tells us if the series with the absolute value converges, then you can conclude that the series without absolute value bars converges as well. So because I know this series converges with the absolute value bars, we can conclude by the theorem for absolute convergence, the series without the absolute value bars, sine n over n squared, must also converge. So this theorem is particularly helpful if you have a series whose terms are some are positive and some are negative, because when you apply the absolute value bars, you know that everything in the series becomes positive, and that might help you create a bound. Because the whole way that we were able to approach this is that we're able to bound the sign function, which then led us to this inequality that enabled us to use the direct comparison test. So a little bit earlier, we talked about how when we're using these tests, we have to pay attention to what the condition is that we must meet in order to reach a conclusion, because we cannot switch those two things around. If I were to switch those two things around, it would not be true that if I have a series that converges, that does not necessarily imply that when I apply absolute value bars, the series will then converge. For example, in number 2, we looked at the alternating harmonic series. The alternating harmonic series was the series -1 to the n multiplied by 1 over n. We concluded by the alternating series test that this does converge. In fact, there's a blank right here to write it. The alternating harmonic series is the series -1 to the n multiplied by 1 over n. We know that that series converges by the alternating series test. But remember that the harmonic series, just the original harmonic series, this diverges by the p-series test. Once you apply absolute value bars to this, you get the original harmonic series, which does not converge. It diverges. So you cannot say that if a series converges, then when you apply absolute value bars, it will also converge. This is not true. So you have to pay close attention to what condition you start with and then what conclusion you can reach. And now we have some definitions. We define a series as absolutely convergent if the series of the absolute value of the terms of that series converges. If when we apply an absolute value and make all of our terms positive, if the series converges, then it is absolutely convergent. Mind you, an absolutely convergent series, we know from the theorem above, from this theorem, we know that that implies the series without absolute value bars converges as well. So if a series is absolutely convergent, it is also convergent without the absolute value bars. If a series is conditionally convergent, what that means is that the original series converges, but when you apply absolute value bars, it diverges. Like what we saw with the harmonic series, with the alternating harmonic series. The alternating harmonic series converged, but when we apply absolute value bars, the -1 to the n goes away because the absolute value of that would just be 1, and that diverged. So the alternating harmonic series is an example of a conditionally convergent series. In the remaining examples, we're going to test whether or not these series are convergent or divergent. If the series is convergent, we'll determine is it absolutely or conditionally convergent. Beginning with example 5a, this is an alternating series because we do have this -1 to the n. So I will try the alternating series test. Everything else that is left in the series, I will select to be my a sub n. I'm going to calculate the limit as n goes to infinity of n factorial over 2 to the n. If I were to look at the terms of these of this sequence, we would see that factorials grow faster than exponentials. And if the numerator is growing faster, that means that this limit is infinity, which is not equal to 0. So I am not able to use the alternating series test. The conditions of the alternating series test were not met, so I cannot reach a conclusion. So I'm going to go try a new test. If I have to start from scratch and try a new test, I would start with the nth term test for divergence. The nth term test for divergence tells me to take the limit as n goes to infinity of everything that is on the inside of our series. In taking this limit, I'm going to separate it into a product of two limits, because in the second factor, with the n factorial over 2 to the n, we've already said that this limit here is infinity. If this goes to infinity, there's no way that this entire limit equals 0, especially with this factor right here doing nothing but alternating, with that limit not even existing, going 1, -1, 1, -1. So if that limit does not equal 0, then the nth term test for divergence tells us that this series must diverge. Because this series diverges, we do not even need to explore if it is conditionally or absolutely convergent, because it's not convergent, it's divergent. Let's look at example 5b. Again, this is an alternating series. Because I have this -1 to the n, I will take everything else that is left in the series, which is a square root of n in the denominator. You can imagine there's a 1 in the numerator above that. So a sub n will be 1 over the square root of n. Let's check the alternating series test. So now I'm going to check the two conditions for the alternating series test. Does the limit as n approaches infinity of a sub n equal 0? It does, because the limit as n approaches infinity of this rational expression has an answer of 0 since the degree of the denominator is greater. The second condition for the alternating series test is this sequence decreasing? Is the nth plus 1 term of this sequence less than or equal to the nth term of this sequence? And it is, because the nth plus 1 term has a larger denominator, which does mean a smaller number. So since these two conditions of the alternating series test are satisfied, we can conclude that the series converges by the alternating series test. Now let's determine whether the series is conditionally convergent or absolutely convergent. It will be absolutely convergent if the absolute value of the series also converges. When we apply the absolute value, the -1 to the n is just a 1, because the absolute value of -1 or 1 is just 1. And in the denominator, we have the square root of n, which is always positive. So I don't need the absolute value bars there. So what is the behavior of this series now? This is a p-series. It may be helpful to rewrite this series as 1 over n to the 1/2, so that you identify it as a p-series, where p is equal to 1/2, which is less than 1. Which means that that series will diverge by the p-series test. So we have seen that when we apply the absolute value bars, the series diverges. So it is not absolutely convergent. If it were absolutely convergent, the absolute value series would converge. So I conclude that the series is conditionally convergent because it does converge when the absolute value bars are not there. So it only converges conditionally. In example C, it's important to note that I don't necessarily know, looking at this, whether or not this is an alternating series. So look at the difference between the factor of -1 with an exponent in example C and the factor of -1 with an exponent in example D. With this -1 to the n, I definitely know that this series is alternating. I know one term will be positive and I know one term will be negative. Over here in example C, I don't necessarily know that because this exponent of n times n plus 1 divided by 2, we need to check, does it give us even values and then odd values, or does it give us even, odd, odd? So let's take a second to explore the terms of this series to figure out whether or not it even is an alternating series. So when n is equal to 1, I get -1/3 out. I'm going to now evaluate the series when n is equal to 2. I get -1/9. When n is equal to 3, I'll point out, I could stop right here. Like with this series, getting a negative term and then a negative term, that is not an alternating series. If I were to evaluate the series at n equal to 3, I would get a positive 1/27. And I'll just put plus ... but I can conclude that this is not an alternating series because it does not go positive, negative, positive, negative. So I cannot use the alternating series test. So since I can't use the alternating series test, and I have this factor of -1 that shows up in the numerator, I am going to start by testing the absolute value of the series. Because when I apply the absolute value, we eliminate all of the numerator and simplify it down to a 1. In the denominator, the absolute value of 3 to the n is simply 3 to the n. So when I apply the absolute value, I simplify it down to a very simple geometric series where r is equal to 1/3, which is less than 1. And so I do know that the series is absolutely convergent. Because when I apply the absolute value, the series converged. If it's absolutely convergent, mind you, it is also convergent. With this also converges. That's from this theorem, just as a reminder. So sometimes when you have a series, particularly if it's not an alternating series, but it has something like what's highlighted in yellow showing up with that -1 to some weird exponent, it may be helpful for you to choose to come in and apply these absolute value bars. Because once you do that, all of this just simplifies down to a +1. And you get a much simpler series that if you're able to conclude that that series converges, then you know that your original series is also convergent.